All right. Good evening, everyone. Good afternoon. I'm so sorry. We're just trying to sort out the visuals over here. They couldn't clone my screen. Probably I'm the only one who's potentially doing a demo on screen, and nobody's used the laptop so far. So sorry about that, everybody. But first things first, how are you guys having a good Hadoop Summit? Come on, guys. You can be louder. How's the Hadoop Summit been? That's more like it. Thank you so much. All right. So we're here to talk about big data application architectures for IoT. I'm Nishant Thakur. I'm the technical product manager for big data analytics at Microsoft. Work closely with customers, with engineering teams to make sure our products have the right messaging as well as come out the right way as customers expect them to be, right? Now, as part of my job, I deal with a lot of customers and their engagements as well. And what I've tried to bring about in this session is some of the common patterns and how customers look at implementing IoT solutions using some of the services. Right now, just a disclaimer over here. I have expertise around the Microsoft stack, so Microsoft set of big data services and mostly on the implementation with the cloud. But as we go along, things that I discuss and reference with some of those services definitely are extensible to some of the other clouds. Now, a shameless plug, they work best or they work much better or are much closely knitted together with the set of services that I'm going to talk about. So if you have any questions around any of the alternative services, feel free to put up your hand. We can take questions or we can wait right till the end, right? Now, let's really rush in. I think I've lost about a good amount of time, so I should make sure I get through the content as well. Phew. Please. Okay, forget this. All right. On the agenda, it's the simplest that one could have. We're going to talk about architecture, so we're going to talk about the why, what, and how, all right? So the first thing that we're going to talk about is why is the world crazy about IoT today? Why is everybody talking IoT? What does it actually mean? And potentially, if time permits, I can show you an example of that as well. Then it's the what, that's the biggest piece that we're going to go discuss in our session today. And then how is like the principles around designing some of these as well, okay? Now, as we discuss with customers, the most important thing that comes across these days is what's the importance of data today? And I thought it's important that I put this across. Well, Peter Sondergaard from Gartner mentioned about a couple of years back, in fact now, and it still stands perfectly fine. The information is the oil of the 21st century, and analytics is its combustion engine. So what we're looking with all of these sensors and devices sending up data to the cloud or to their respective environments, we're looking at all of this data leading to a complete revolution in the way we consume data and the way we convert it into intelligent action as a whole. So I think this is going to stand good for probably the next about 50 years until the next revolution comes in. As they say, the first revolution was about the coal and the steam engines, and the second one was probably about the computing power or the computers, etc. This is what we're looking at as potentially another revolution with data and IoT as we go ahead and consume all of that data as it comes in. Just to give you a glimpse of the number of connected things that we have today, it's probably exceeded the number of toothbrushes that we have in the world. Well, again, figures from Gartner, we've got about 4 billion toothbrushes in the world, and we're looking at already over 5 billion connected devices today. And by 2020, that's bound to reach about 25 billion connected devices. Now, with connected devices, what I mean is you're going to have smart socks, smart toasters, smart ovens, probably even smart machines and smart toothbrushes, etc. But taking more seriously, you're going to have automobiles that talk to a lot of systems. You're going to have cars that are self-driven. You're going to have bots that are governing the way we go ahead and do our jobs, as well as help us achieve more and do more. Now, just to give you a glimpse of what we think about as part of IoT, where you're looking at a picture in the life of a day of an individual. Just look at the amount of data that's getting generated every time you're walking around, consuming any kind of information, or connecting to any kind of network, or consuming any of those services which we do in our daily lives, right? So, passing a signal, that generates data. Talking on the phone generates data. Carrying a cell phone generates data. In fact, every time you walk about a kilometer with a phone, you generate about 2 gigabytes of data for any of the mobile providers that you're connected to. So just imagine the amount of data that you're generating and the kind of insight all of that data can give about you as an individual. Now, taking it a little further in the form of customer examples, and again, disclaimer, these are just customer examples. These are not Microsoft customer references, all right? Now, you've got all of these customers using data from devices and connected sensors in very innovative ways. You got one of the companies using plugs which are digital to go ahead and generate data about how their cylinders or how much of the cylinders are consumed, et cetera, or for how long have they not been filled up or refilled. You've got, of course, organizations or companies like BMW creating smart cars, which are, at least today, they are assisted driven, and probably tomorrow they'd be self-driven in themselves. You've got organizations that are creating devices that can be plugged into any of those machines and generate more data about any of those individual pieces inside of those machines. So, for example, you've got trucks, you've got sensors within those trucks, and you're generating data from those sensors to be captured and analyzed in real time. Again, you've got DHL, you've got Daimler, who are doing wonderful things with it. Now, just to give you a quick example of the kind of stuff that people are doing, I'm going to go ahead and bring up my screen over here, and here's a sample app that one of our customers has built a solution around. Now, what you see on the map over there are actually locations of trucks that are getting tracked. All of these trucks are currently on the road. Each of these trucks have hundreds of sensors in them, and each of those sensors is sending out a data point every second, and every 10 seconds, you get about 50 additional data points from this particular truck. Now, just imagine the kind of insight you have into the working of an individual truck with that kind of data coming off in real time to you. Just multiply that with about 58,000 trucks that this particular customer has on the roads. And you definitely have a problem of big data. Because one, the volume of data that you're dealing with in a very short span is beyond what the traditional or relational methodologies can handle. Second, the format in which this data is produced is sometimes not conceivable by those systems. And third, you need to have insight into the data that's coming in absolute real time. Because if you get historical analysis, that's no good for these kind of scenarios. Now let's actually go ahead and dive into, and as we speak, you saw one of these trucks go red. Well, what does this signify? It actually signifies that on the basis of sensor points that are coming across on the truck, machine learning algorithms predict that the freight contained in those trucks will not reach its destination safely or will get spoiled. Again, on the left-hand side, you see tiles, which are giving you real-time windowed feeds into the data that's coming in and aggregating all of that for you. Just imagine, all of that aggregation across 58,000 trucks with data coming in every second from about 100 sensors on every truck. And all of that happening in real time for your dashboard over here, and you getting a summary of it in no time at all. Now, that's just not all. Well, you'd say, is that the only information that you're consuming? Not exactly. I'm actually consuming weather data on top of this, which is immense in terms of the size that it comes with and the format that it comes with. And for you to be able to map it and to make sense of it in relation to all the data that's coming in from the trucks is, again, an enormous task. Well, if I dig deeper, I can actually see that I'm tracking the traffic on the roads at this particular instant via the map APIs. And all of that information is being tracked back to my machine learning models that are letting me know whether there is a traffic jam, or is there any sensitive data contained in the trucks, or how's the temperature doing in the area, or how the various parts of the truck doing, and whether my freight's going to reach its destination safely. Now, let's dive into one of these trucks, actually. Let's go ahead and see what's happening with one of them. So here I can actually go ahead and dive, and I've dived into a truck which is showing negative outcome prediction, right? So I have this truck over here. I can go ahead and click on any one of these sensors to actually see all that data being streamed across in real time for me to consume. Now, it has a threshold, and what you're seeing over here is actually not the data coming from the truck, but it's actually a prediction for the next 4 hours on what that sensor reading could be like, based on all the factors that we discussed on the previous page. So just imagine the kind of sophistication that organizations are building into their data consumption methodologies and what IoT can actually assume. Over here, you know this truck is red. You know the freight or a part of the freight is showing up as red, which means it predicts that the food is going to get spoiled. So in essence, you want to go take some action so that it doesn't, since it's a prediction for the next 4 hours. So you can go ahead and determine what's the reason why it is getting spoiled. And here you see that machine learning predicts that the fan speed of the cooler is showing some abnormal behavior, and it's going to come down to 0 over a period of time. As a result of which, the cooling unit's temperature will rise beyond the threshold, and your temperature-sensitive fish, or fish for sushi, is going to get spoiled, and it's not going to reach its customer or its destination. Now, you want to go create a task and make sure that that doesn't happen. But before that, these are all sensors, are battery-operated sensors. How much can you trust the information coming from them? Every time you want to go take a decision based on them, you want some kind of anomaly detection to determine if the sensor is working fine. So even that is something that can be built with machine learning algorithms on top of the data that's coming in from the sensors, and everything in real time. Again, I can join it with data coming in from CRM systems to determine if the value of the freight getting spoiled is big enough. And then when I determine I need to take some action, I can go ahead and create a ticket, divert the driver, alert the depot as well, and then confirm and notify the driver over here. Now, the driver may have something like this sitting on his phone. Well, as you confirm and notify the driver is going to receive a notification over here, which reads probably around how this is happening for the driver. So let's just go ahead and click on OK over here and say, well, I accept whatever recommendations that you're giving me as part of all of these analysis that you have done. Now, it could be a diversion in the map for the route. It could be sending some technician to make sure that it's taken care of inside of wherever the nearest depot is. Or it could be about replacing the trailer as is. But in a way, you're saving the business millions of dollars over a period of time when you implement such a solution, right? Now, let's just talk about the technology that's running at the back end. Well, you're dealing with thousands of devices, so many sensor points, terabytes of data every hour, well, you cannot go ahead and implement a custom solution around this. You need to make sure that you're using something that's scalable and that can be scaled across on the cloud as well. Here, in this case, we're using Storm to go ahead and capture all of those events and provide you with the insights on the KPI summary dashboard with windowing operations working inside of them. All of that data, after being processed, is actually being sent to a HBase environment inside of HD Insight. And this particular app is actually querying that HBase in absolute real time with SignalR queries as we speak. Again, Storm also has a bolt which is calling a machine learning model that's already been created and published to be consumed to get predictions upon receiving any of these data points. So you're integrating real-time analytics, aggregations, you're integrating machine learning, predictions, you're integrating a storage environment, and you're integrating a workflow-based schedule over here so that you can come in with all of this integrated inside one particular solution. Now, that's the power that big data can bring to an IoT solution. Well, that was just an example. And let's go ahead and see how we can actually go ahead and implement one of these. So the next point on my agenda is, what do some of these solutions look like? Now, when we look at a typical reference architecture of one such solution, here it is. Now, again, any customer implementing any kind of IoT solution would definitely have at least one version of this reference architecture implemented. Now, what are we talking about on this architecture? I'll start from the left. There are a ton of devices that we are talking about. All of these devices definitely need to be able to connect to some kind of data store. It could be via directly connecting to the data store, or it could be via connecting to a gateway and through that gateway onto a data store. But all of them need to be connected. Now, these connections can happen via protocols that are near in terms of the bandwidth that you provide, or it could be long-term in terms of the reach that that data point has. Now, when you're looking at each one of these protocols, you determine the kind of devices that you use. The second part is the gateway. Well, you need to understand that only your devices are connecting to your gateway. You don't want to go consume data from the rest of the world, because you're not going to be able to make sense of it unless you've architected that inside of your solution, all right? So that's the gateway that's going ahead and identifying whether the device is actually consumable within the solution and consuming the data, or at least buffering the data inside of it. Now, these could be any of those ingestion engines, could be Kafka, could be the IoT hub on Azure, could be the event hubs as you bring in the data. The second part of it is to make sure that you are understanding the data point that's coming across from these devices. So that's more about connecting the data point to some certain reference data that you have about those devices. For example, the units, the make, or let's say, for example, if there are any adjustments that need to be done on the readings because you've identified that that particular sensor is off by a certain mark, okay? And that's where the registry stores come in, which store all of this metadata and can be combined with the data that's coming from the sensors. Now, at that point in time, you also want to understand if those sensors are working fine or not. So that's where you go ahead and determine or make a decision on the validity of that reading and store that particular validity decision as part of your device state stores, right? So you know whether your devices are working fine or not, okay? The next piece is, you've got that data in real high speed. How do you go aggregate or perform analytics on top of that data to be consumed as part of your information? That's where the stream processing engines come into the place. The likes of Storm, Spark streaming, as well as probably the Azure Stream Analytics, which is an extremely easy to use SQL syntaxed streaming language inside of Azure. The next piece is either you go ahead and consume the results of that stream process inside of one of your dashboards, as you were seeing in one of those applications, or you go ahead and store that data inside of a data lake to be analyzed further later on and to be fed in to train your machine learning models to become even more efficient. Usually, customers would want to go ahead and do both. So they would want to consume information coming in, as well as store it for further analysis. And that's where the connectivity of these streaming solutions to some of your publishing environments is really, really important. Now, the next piece on the reference architecture is the data lake. Now, the data lake needs to be a hyperscale store that can consume data at such high throughput, as well as allow you to process that data as it is coming in. And it needs to be flexible enough to store the data in its native format and be able to allow you to process the data using tools that you like and you're comfortable with. That's where the box to the right of the data lake comes in, the analytics and the machine learning pieces. But you want to go ahead and consume a ton of tools. You want to write Hive scripts, Pig scripts, you want to write Storm on top of it, or you want to go ahead and write Spark or use your notebooks around it, or probably even use your custom applications to go ahead and talk to all of that data. To be able to do that, the data lake has to be open, extensible, as well as very flexible. And that's the important piece. As part of the analytics and machine learning, you're going to do a bunch of activities which are high scale and high throughput as well. So you're going to bring in tools like Hive and Pig and Storm, and probably even some custom tools like any of the in-house built, or some of the specialized tools like UseSQL that's present within the Azure Data Lake. And we talk about that a little later. But as that data is processed and you have machine learning models consuming them, be it R models or Azure machine learning models, or be it Spark ML models, or be it Mahout models, you want all of that understanding of your data to be fed back into the systems. Well, that's where the application backends really shine out. Now, mind you, these are not general application backends that can go ahead and consume data as in transactional systems. Since you're doing a scale-out architecture in terms of high resiliency as well as extreme throughput, you need specialized app backends which are also parallelized in their compute and executions to take advantage of all of that information coming across. And of course, the next piece is to go ahead and consume it using one of the solution UX or any of these business integration connectors, etc. Now, this is one view with a set of technologies that can be worked together on either of those blocks. For example, on the gateway, as I mentioned, you could get Kafka in, or you could get the Azure IoT hubs in, or the event hubs in, to go ahead and stream in or ingest in all the events. For a metadata store, you definitely need something that's flexible enough such that it is NoSQL in nature. So it could be a document DB store that's in there. For any of the transactional data that's coming in, you could go ahead and use a SQL-based store so that there is ease of querying into that environment. For any of the stream processing environments, potentially you could use Storm or even Spark streaming in addition to, Azure Stream Analytics, because it's easy to use. Again, coming in from the data lake perspective, you have the choice of Azure Data Lake or the blob stores across any of these clouds. Coming in from an analytics and machine learning standpoint, again, You can use tools within the Hadoop ecosystem, the Spark ecosystem, or any of the machine learning tools to work on the data residing inside of your data lake, as well as interact with the stream processing engines to give you real-time analysis on all of that data. Coming to the back end, it could be service fabrics, or it could be batch processing tools that could be used to go ahead and extrapolate your compute across multiple nodes over there. Now, let's go ahead and discuss individually around each of these pieces somewhat. When we look at the device connectivity options, now, this is another very important piece that comes in, because how are you going to stream that data in the first place? How is that data coming across? What are the kind of protocols that you're going to use? And what are the methodologies that customers are using today? Well, in essence, we look at about 4 such patterns for device data coming into the hubs. The first one is, of course, some of the customers are self-equipped, and they want to go write their own custom solutions around it. So each of those sensors definitely can produce data, and they want to go write protocols for themselves as well as gateways of themselves and consume that data. But the more generic ones are the two in between. One being that you have that IoT client, and that IoT client is directly connecting to your gateway, be it on the cloud or on-prem. Okay? And all of these gateways that we talked about in the previous slide definitely have the capacity to go ahead and consume data, or at least ingest data, in massive amounts at the right velocity for an IoT solution. The third one over there is that sometimes you have too many devices localized inside of one environment. And that's when you actually want to go ahead and create a device, a field gateway around that environment, so that you're not streaming those individual data points individually, but you're streaming them as one single tuple that gets consumed, and as such, it reduces the computations that you have to do for each and every sensor point as it comes. And usually, probably 70% of all solutions are built around this particular principle itself. And of course, there's another one of those where you want to bring in all of your data onto your field gateway, but still have a custom gateway for encryption needs or masking needs or whatever there is before your sensor data is coming across. Usually, this is the case with medical devices, where they are associating any kind of patient information, et cetera, and they want to go anonymize that data. That's where a custom gateway comes in between before it enters the generic gateway. Now, that's the left-hand side piece of the reference architecture. How does that data come in? And of course, there are a ton of protocols that you can use. You can use MQP or MQTT or HTTPS, and each of those are sufficiently provisioned inside of the IoT clients, inside of the devices or the sensors, as well as on the gateways that we talked about. As we get into the device stores, the important piece is to understand that the gateways are also the identity stores for these devices. So as I mentioned, you need to check that you're consuming data only from your device. You just don't want to go ahead and consume all the data that's coming in and forget about the device identity, et cetera. Of course, you're going to go ahead and check up on the meta store and bring in all the reference data as well, and provision the APIs to make decisions around it. Just a little more details around the identity store, registry store, and the state stores. Again, repeat of the information, authoritative for registered devices, indexing in the registry store, and then operational in the state store. Okay? When it comes to some of these stream processors, which is potentially amongst the most important pieces of an IoT solution, since you want to consume that data and make decisions based on that data in absolute real time. Here is what you would be doing ideally with these stream processors. So you would be bringing in the data, you would be aggregating and consuming or even sometimes cleansing the data. You would be sending this data to models to be extrapolated or done some predictive analysis or prescriptive analysis upon, and then sending the results of these models back to your clients or to your data lakes to get consumed. Now, when you look at options that you have for it, of course, you got a bunch of streaming solutions available, and I've just quoted a few up there. You can think about 100 other streaming solutions and plug them inside of the same environment over here. But when you look at the kind of operations that these stream processors actually go ahead and accomplish, that's amazing, the kind of work that you can do with the data as it comes in with the entire velocity of thousands or even millions of events a second. You can go ahead and process the metadata. You can go ahead and process the device state. You're doing notifications and messaging on that data. You're even going ahead and bringing about rules within the processor. And you're bringing about stream transformations from the processors as well. Now, when you look at the kind of environments that accomplish these, they're usually in two categories. One is real streams, the likes of Storm, which consume data in real streams and go ahead and process them as a true streaming solution. And the others are micro batches, which potentially just go ahead and consume all of that data and leverage the buffering capabilities of the gateways, such as Kafka or IoT Hub, etc., to go ahead and convert them into very tiny batches and process those batches together. And the micro batching is getting more and more popular as a solution because it's easier to implement, and you can still use all of your capabilities of batch mode querying and processing on top of the streaming solutions. Because the streaming solutions, the native streaming solutions, are typically a little more difficult to go ahead and program around. Okay? Now, I'm going to go skip on the app backend over here because, of course, that's more about compute models, and everybody understands how some of those compute models would work. So you could have active frameworks or service fabrics working across them, or you could also go ahead and write your custom MapReduce programs or custom Spark environments to implement your programming language in scalable compute nodes around it. Now, the important part around how big data plays a major role, apart from, of course, streaming being a major component of the big data ecosystem as well, is that how are you consuming all of that data? Where are you storing that data? How's the data flowing across in your environment? And what kind of tools are you using on it? And how are you feeding that back to some of my corporate information so that it can be reported in conjunction with some of the transactional data, as well as some of the immense amount of data that you possess otherwise. Just to give you a view of such an environment, we've put up this particular picture here. If you pay attention to it, it is nothing but a representation of how a customer would go ahead and implement their entire data environment to consume and make a lot of sense of all of these devices. The data comes in from all of these sensors, goes into event hubs or ingestion engines, gets inside stream processing engines, which could be any of the stream processing engines. In addition to being processed as aggregators, there are certain relational stores being referenced as well for reference and registry data. All of this data, combined with predictions from machine learning models, is then stored back inside of your data lake. In our case, the Azure Data Lake store. Now, once it's there, you can use a plethora of tools. You can use SQL, which is part of the Azure Data Lake analytics stack. You could use Pig. You could use Spark to go ahead and process that data and consume that data. In addition to that, you can source all of this data residing inside of your data lake store to your machine learning environments to consume and process models around them. This is training data for your models. This is events that have actually happened, historical data for your models to consume and then understand patterns within. These could be models working inside of R and scaled across a Hadoop cluster with R on HD and Site, etc. Or it could be R working with Spark on HD and Site, etc. And then you could use tools like Azure Machine Learning to go ahead and operationalize this, which means you just go ahead and publish these as models to be consumed as API services with the click of a few buttons and not having to write wrappers on top of them. And then, once you've consumed all of that data and trained your models, they are more intelligent to first source it back to your stream processing, and second, source that data inside of a warehouse for you to consume on demand. Now, once you've done that, you can have a reporting environment which can consume data directly from your big data stores, probably using connectors like Spark onto your BI tools, or it could definitely connect back to your data warehouse to consume the data on demand. Now, that's an end-to-end solution that you would go ahead and implement for an IoT environment as a whole. Again, when you look at data analytics, you're looking at a few tools over here. The real-time analysis piece, the data at rest analysis, as well as the immense amount of machine learning that plays a role with IoT solutions, be it pattern detection or behavior predictions or plausibility analysis or even anomaly or fraud detections within the environments as the data comes in. Now, I've talked about a solution all this while. Let's go ahead and talk about an environment that can actually bring about all of those tools together and make it easier. Here you've got the Azure Data Lake. You can go ahead and utilize the storage capabilities to bring in data, be it tuples of sensor information, or be it petabyte-size files. Individual files of petabyte size can be brought in at one go and stored as part of your entire historical data. You have tools from an analytics standpoint waiting for you to work upon that data, be it using the job services like analytics, or be it using cluster-based analysis tools like Hadoop or Spark or Storm or HBase, or whichever animal in the zoo that you want to go pick up from the open source world. Again, that's not all. It sits as part of a suite that enables you to surround it with an ecosystem of all of these services such that you don't actually have to worry about stitching each and entire solution together. It's already there for you. So be it about bringing data in, or be it about storing it in a store, or be it about analyzing it, or be it about adding cognitive capabilities, or be it about automating the processing using bot frameworks, or be it about visualizing the data after all of this is consumed in immense high speed and real time. And that's when it actually enters your business connectivity pieces as well. How does this data get consumed? Once you've analyzed, for example, all of those trucks' information, how do you send it back to some of your systems to be consumed as part of your business processes. The APIs that are enabled around all of these services allow you to go ahead and enter all of that data inside absolutely seamlessly. Now, once again, just putting across the ref arc over there for a preview of what we just discussed. And the next point that we get to is just the guiding principles around such an architecture. The 4 guiding principles that govern any such reference architecture are definitely how you go ahead and make this environment heterogeneous such that it accommodates hybrid, cloud, and on-prem environments. How do you play around with security? Well, there's a concept called trustworthy computing within Microsoft, that before we go ahead and release any service, we have to make sure that it adheres to a certain protocol that we want to set for ourselves as well as for our customers. And as custodians of such solutions built on the platforms, we definitely encourage all of you as well to go ahead and think about how these devices can become secure and these processes are not easily hacked. Because the implications that such environments have for the overall population is absolutely massive if anything goes wrong. When you're looking at the scale, you definitely want to make sure that the services support millions of connected devices, as well as the solution is catered towards processing them all. And then, of course, the flexibility. Well, that's pretty much all the content that we had, just in review. We discussed why IoT was important. We discussed what a reference architecture would look like. And in turn, we also discussed how we should go ahead and think about some of these applications and solutions on top of it. Just remember, as we speak, by 2020, you're going to have about 7 networked devices per human being on the planet. So imagine the amount of data that you will have to consume, process, and analyze, which is an amazing challenge to have, but a big responsibility as well to make sure that we live up to the expectations. And again, coming up on the number of sensors, there are about 200 billion sensors that we'd be dealing with. With that, I just pull it off to a close over here and open it out for questions and answers. Got a few posters up here around the entire stack if anybody wants to grab one and take them with yourselves, and we can talk a little more around these solution aspects as well. But thank you so much for staying back on the second day so late in the afternoon, and I hope you got some value out of this session. Thank you.